Hi everyone, welcome to this session on brief introduction to computer vision. I hope you've been learning quite a lot in the Kaggle Days meetup so far, and we hope to keep up that same spirit in this brief session. Okay, so before we start, let me quickly introduce myself. My name is Rajneesh. I am currently working as a data science solution architect with Ericsson. I have experience in both the consulting side, ML consulting, and building products. So I've worked with organizations like GS, Associates, WNS, and Ericsson in the past. I'm a Kaggle competitions expert. I'm currently ranked top 1%. I've got 4 silver medals. And one thing I want to say here is that I also try to mentor folks who are either trying to get into this field or are already in this field. So if you feel the need to learn new stuff, or if you're stuck anywhere in your data science journey, so feel free to reach out. I'll be listing out my contact details in just a bit. In terms of education, I'm IIT and ISB alumni, and I've posted here my email and LinkedIn addresses. For you, if you want to reach out to me, you can reach out to me over either of these channels. Okay, so let's get started now. So what is computer vision, first of all? Uh, Now, the goal of computer vision is to basically write computer programs that can interpret images, right? Now, the one question that obviously comes to mind is why do we need to interpret the images? So for that, just to understand why do we need the interpretation part here, right? So if you look at the image on the right hand side, right? So it has it's image of a building, probably close to a river, and you have a couple of the vehicles, cars, right? And you have trees and so on. Now, anybody who's looking at this image, right? They can ask a number of questions. So first question is, what kind of scene is this, right? Where are the cars, and how far is the building? So these are some of the examples of questions that can be asked by looking at these images. Now, in order to be able to answer these questions, our code or our model should have a very good understanding of what the image represents, right? What are the various entities in the images, where they are, what is the depth of the image, right? Depth of the various objects in the images, and so on. So, and hence the need to be able to interpret these images in the right context, right? Now, one thing I want to point out here is that many a times computer vision kind of gets confused with the concept of image processing. So image processing is an entirely different concept in itself, which deals with kind of manipulating the images themselves, right? So we don't generally build models when we're working in image processing, but we try to do a lot of stuff with images themselves, right? So we do some kind of transformation, some kind of spatial transformations, and so on, so that we get to a whatever the task we're trying to solve. Right? So we get to a better image quality in that sense. In computer vision, our task is entirely different. We're trying to build models or write code that can interpret the images in the context of a particular question that is being asked, right? Uh, the other thing is, lately there have been a lot of concepts from image processing that have started coming into computer vision part as well, right? Because computer vision part obviously involves using a lot of images, and not just images, but at times you also deal with video data. So if there are some specific transformations that can help you get to a better accuracy or better model, then you would obviously try to deploy them, right? And a lot of these transformations, or at least the inspiration for those, is coming from the image processing part of things. Now, so the other question is, why has computer vision become so popular now, right? And the first reason that it has become so popular now is that there's a lot of image data that is being generated. Not just image, rather a lot of video data also that is being generated. Now, what are the fields that are kind of leading this space in terms of images? So first is your medical science or medical imagery data. So a lot of hospital chains, clinics, right, and a lot of foundations, they're kind of outsourcing this data to leverage AI and machine learning to build better models for their purposes. So There's this competition right now, I think, going on in Kaggle, which deals with uh, detecting blindness in diabetic patients, right? And they have, and this it's hosted, I think, by one of the hospital chains in India, and they've provided a lot of retinal scan uh, of the patients. So that's a very good thing, right? So if they get a model which can outperform their in-house doctors in terms of detecting these uh, this kind of symptoms, then it's very good for them, right? So they save a lot of money, they see a lot more patients because now they're using some kind of automated tool. So it helps everybody in the end. The second is the satellite imagery. So there's a lot of satellite imagery around, I would say, environment conservation efforts, and it has applications even in defense and robotics, right? So tasks like detect if you are able to detect what kind of how the landscape has changed over a period of time, right? Suppose you're given satellite imagery of say Amazon forest, right? Say and say past 5 years data. And if you can detect how the satellite imagery or the landscape has changed over a period of time, then you can detect a lot of things like say whether there's a lot of deforestation taking place, or whether there's been a lot of illegal mining activities and so on, right? So computer vision models come in handy in a variety of use cases. Third is obviously you have now a lot of image data being generated and stored on the web. So if you want to build a model that kind of customizes to your objective, and if you do not have a ready-made data set for it, you can obviously go to web and search for images and download those specific images that you want. So just to give you a pointer here, not sure if everybody here has heard of FastAI, but FastAI is led by Jeremy Howard, and I think, in one of his classes, he demonstrated a script as to how one can download images from the web based on particular categories that you're looking at, right? So suppose you're looking at say pictures of want to download pictures of dogs and cats, right? And you want to classify them in the end, obviously. So that script can help you out download these images from the web in a kind of without using the manual effort. So you can just run the script and it will download relevant images. The last is obviously there's a lot of data from internal systems of a company that is being generated specifically for computer vision use cases. So think of say a retail company, right, which is trying to solve a problem called bottom of the basket. So we'll get into what that is in a couple of slides. For now, just assume there's a problem called, or there's an issue of bottom of the basket analysis that is very prevalent in retail industry and leads to like millions of dollars of loss every year. Now the companies will start capturing this bottom of the basket data set specifically for their models to train, right? Similarly, think of a telecom use case wherein a telecom operator is taking pictures of say your mobile towers and trying to identify faults within the tower just by looking at the image, right? So these specific use cases, they enable companies to capture, to kind of build systems that are able to capture images, and then they try to solve this very specific use cases by leveraging computer vision models. The other reason why computer vision has become very popular now is that we now have a very good understanding of how to model images into tasks, right? So whether or not, so the task could be something like segmentation or classification or something else, but we now have a very good understanding as to what kind of models do well on those kind of things, right? And we'll quickly also look at towards the end one specific type of or one specific component of these models that has helped kind of revolutionize this field in entirety. The other thing is the concept of transfer learning. So we'll not go into the details here, but transfer learning is like something very big that has come up, and it enables users to leverage models that are trained on a different data set for their own specific tasks, right? So we'll not go into how that happens or why that happens at all. But the idea here is if you have, say, if you're trying to build a classifier, right, based on images, say dogs and cats, and you only have, say, 10,000 images. Now, computer vision models would not generally do well on 10,000 images if you build them from scratch. But imagine if somebody has had access to 10 million images of say a different kind of things, right? So say they have pictures of wolves, uh, say sheep, boats, and so on, right? So, similar stuff, but of a different category class, right? Now they have built a very extensive model on these 10 billion images. So the idea of transfer learning is that you can use that better model that is trained on a lot more images for your own specific task of detecting cats and dogs. The last thing is obviously a lot of growth in compute power recently. So now specifically on the GPU part, so now you have access to very cheap GPUs on Google Cloud or AWS or even third-party providers like say Floyd Hub, and there are a couple more. I'm forgetting the name. Yeah, I don't remember the name, but yeah, these three come to my mind right away. The other option is obviously if you want to do computer vision in a dedicated kind of a way, you can also try and build your own machine. So there are GPUs, so you have 1080s, 1080 Ti's, and so on that you can. And there's a lot of material over the web to help you understand how much power you need and what kind of things you want to do, right? So you can also build your own machine. That's a second option. Okay. So essentially, how does computer vision model work, right? So like any deep learning model, and again, if you're not familiar with deep learning, don't worry about it. We might cover those things in one of the future meetups. So in deep learning or in computer vision models, right, what essentially are we trying to do? So we have the input images, right, and we have the outputs also for the training part at least, right? We need the inputs and the outputs. So outputs could be your images or your masked images or your class labels, right? So depending upon whatever the kind of task that you're trying to do. Now, with these two things, we essentially try to come up with the best model weights or model parameters, as we call it. And what these model parameters do is help you interpret the images in the context of the output, right? So we said at the beginning that the goal of computer vision is to create models that or write codes that help us understand the image themselves, right? And these model weights, they help us understand the images in the context of the task that we're trying to do. And this is also like one difference vis-a-vis image processing part. So in image processing, we do not have the model weights or model at all. What we have is like input and then some transformations and then the output, right? The output is obviously unknown to us at that point. We try to do some kind of transformation and see what outputs we are getting and whether or not the output is suited to our task. Okay, so what are some of the common use cases of computer vision? So first, and probably one of the most earliest ones is called optical character recognition. Now, optical character recognition is nothing but it's a technology to convert scanned documents to texts, right? And two most prominent use cases here are license plate readers and digit recognition, right? So license plate readers are basically systems that take a look at your license plates, right? Which is like taking a snapshot of it and then converting them to relevant digits and alphabets. So if you live in any metro city in India, you must have seen on highways, right? So they have these systems that are installed and they continuously take snapshots of moving cars. And what they do is they register your speed as well as take a snapshot of your license plates. So if you're overspeeding on a particular highway, they would kind of send you an email or a SMS based on your speed, right? And they'll get all these details, your email and SMS or mobile phone details by just by looking at your license plate numbers, which are obviously decoded using the OCR technology. The other thing is digit recognition. So this was kind of made famous by Jan LeCun, who leads AI efforts at Facebook. And back in I think 1990s, late 1990s, I think they built a system that enabled the banks to automatically read the amounts from the handwritten checks, right? So imagine if you're going to a particular machine, maybe an ATM machine, and you're dropping your checks, and the amount on the checks is automatically read through by this digit recognition system. And this model later came to be known as LeanET 5 model. So we don't use it now, but this kind of formed the basis of a lot of improvements later on. Okay, so let's move on to the next use case now. So next we're talking about face detection and smile detection. Right? So in most of the digital cameras or even smartphones, right? Smartphone cameras, there's a face detector, right? So anytime you're taking a picture of yourself or your colleagues, right, or your relatives, right, there's a kind of box that appears around each of the face. So this is called your face detection model, and there's something else also called smile detection, right? So I'm not sure if you've heard about this, but there's a camera. I don't remember which brand it comes from, but the idea is if you're taking a picture of a group of people, right, and if some people in that image are not smiling, then the camera will wait to take a snapshot until everyone is smiling, right? So that's a very good idea. The other idea is about closed eye stopper. I think that's what it's called. So there's a camera that continuously tracks eye movements of people while taking an image, and if during the instance of taking an image, if anybody has closed their eyes, then the photo would not be taken. Rather, there'll be a message that comes up saying that okay, this was a garbage photo, and then you need to take another one, right? With everybody's eyes kind of open. So yeah, these are again very important and very common use cases for from a computer vision perspective. And there are again models that have already demonstrated very good efficacy in terms of detecting faces or detecting smiles or detecting closed eyes and so on, right? So here we already see lots of commercial uses of computer vision technologies being embedded into mainstream products. Okay. The third is about object recognition, specifically in the context of retail industry and in supermarkets. So earlier we spoke about a problem called bottom of the basket loss. So what is bottom of the basket, right? So if you see this image here of a trolley with some products that somebody has bought, right? And at the bottom you see there's a box of Corona beers, I think, yeah. And I don't know what this guy was. Maybe I don't. Probably they were trying to steal it, or it was there by accident, right? So whatever the reason, what happens is this kind of products that are at the bottom, they usually get uh, they are not recognized by the cashier or whosoever is making the payments there, and ultimately, you can steal it, or maybe it gets lost, right? So it leads to a lot of revenue loss for your retailers. Now, what some companies have done, and the company is Evolution Robotics, what they've done is they've come up with a system, wherein they've placed a camera at the bottom here, and anytime you have a trolley that passes here, it takes a snapshot of this bottom of the basket, right? And it continuously recognizes images of products that should not be there, right? And if a particular object is there, then the person who's taking the trolley, the customer, they're charged for it, and yeah, the retailer essentially gets the money for the item, right? So this use case in itself has prevented losses worth millions of dollars for retailers, right? So again, this is powered by a very common computer vision technology called object recognition, and these systems have again proved to be very successful in commercial settings, right? And yeah, the name of the company is Evolution Robotics, and I think the product name is Lane Hawk, right? Okay, now computer vision also helps a lot in terms of biometrics, and a very famous use case of vision-based biometrics is this is a case of this Afghan girl. So on the left-hand side, you see a very younger version of this girl, of this Afghan girl, and she became very famous. I'm not sure for what, why she became famous. Probably for some social issues, or raising some social issues there. But after a point in time, people lost track of her, and then lot of like 20, 30 years later, there came an image of this lady on the right hand side, and people were able to identify that the lady on the right is the girl on the left by looking at the patterns of her iris, right? So essentially, somebody who went into obscurity over a period of time kind of was recognized back, and this was enabled, or this was made to have this was enabled by using vision based biometric systems. Okay, so those are like the couple of very common, or very common use cases for computer vision, especially in commercial settings. Now there's a lot of Other use cases also that we have obviously not skipped, but I want to like quickly cover what are the common tasks. And when we say tasks, we are kind of talking about the technical part of things, not the business use cases. So in terms of tasks, we have three main categories of tasks in computer vision. The first is image classification. So image classification is very similar to a normal machine learning classification model. The only difference is that the input here is image instead of tabular data or NLP data, right? And within image classification, we have either binary, which is 0 and 1, or multi-class classification or multi-label, right? Classification. There could be another one which is which I've not listed here, which is multi-class and multi-label. So what is the multi-label part? I think that's slightly interesting for many folks. The multi-label is basically anytime you have an image, right? And the image can belong to more than one category in itself, right? So uh, one use case that comes to mind is that there was this competition on Kaggle, which was around identifying the class labels uh, in the satellite images of Amazon rainforest, right? And I think what they wanted to do there was to understand what kind of deforestation has taken place, what kind of afforestation has taken place, what kind of illegal mining activities might be taking place at specific places, right? By looking at the satellite images. And any given image was had more than one label. So you had, say, as far as I remember, you had things like agriculture, you had things like mining, and some other categories. Swamps, I think, were there, right? So you have more than one label or one category in any given image, right? So those kind of things are called multi-label classification tasks. The other thing is about object detection. So if you look at the snapshot posted on the right hand side, the snapshot basically shows you some balloons in the air. And object detection is when you want to basically detect the balloons and draw a kind of bounding box around them, right? The bounding box is basically a rectangular box that is around the center of the object, right? And you try to make it as tight as possible, basically touching all the corners. And this kind of task, when you want to do an object detection or draw a bounding box around stuff, that is called object detection. The third is segmentation. So segmentation is very important. In fact, not just segmentation. In fact, let's talk a bit about object detection, right? So object detection is very important in the context of autonomous vehicles. So for example, if you're building an autonomous vehicles, you definitely want to identify what are the items on the street, right? So things like trees, cars, pedestrians, right? You want to be able to identify them and also identify their locations, right? And how do you identify their location is by doing this bounding box kind of thing, right? So all this information needs to be fed in real time to the processing units of the cars, and then they can take particular evasive action or decide the future course of the movement. Yeah. Then we were talking about segmentation. So segmentation is of two types. First is your instance segmentation, and then we have semantic segmentation. So what is semantic segmentation, which is slightly more simpler than the instance segmentation? So semantic segmentation is uh, when you have these objects, right? And all you want to do is basically do a pixel-wise classification, right? Based on the category. So category in this picture would be balloons and say not a balloon, right? So you want to identify the pixel that form part of this object or category, which is balloon, and everything else is non-balloon, right? So here you can see all the balloons or pixel level classification is in blue, and everything else is actually, so we don't care about the other stuff. Now, the important thing to note here is that we are not differentiating between the various balloons that we have, right? So I have a big balloon in between, and then we have smaller ones on the side and so on. But there's no distinction being drawn on in terms of the different balloons that are there, right? So that's where instance segmentation comes in. So instance segmentation is basically not just identifying or not just making pixel level classification, but also identifying the various instances of that class, right? So here you see all the balloons, they're identified by doing a pixel level classification, and are also identified by means of different colors, right? So, and when I'm saying different colors, it inherently means that I have to do a bounding box kind of prediction also, right? Because I need to understand where these different balloons are. So the big difference between semantic and instance segmentation, which which quite a lot of people get confused with. The big difference is in semantic segmentation, you do not differentiate between the various instances of the same object, while in instance segmentation, you do differentiate between the different instances of the same object, right, or the same class. Right. In our context, different balloons, they are identified differently, and the bounding boxes are also identified. Now, obviously, since instance segmentation task is slightly more complex, it is obviously relatively harder to do than as compared to, say, semantic segmentation. So we'll not talk about what models are used in each of them, but if you want to check out the details, you can obviously search over the internet. There's a lot of stuff over the internet for doing any of these exercises. Okay, so I now quickly want to cover one key ingredient of the computer vision model. So at the beginning, we spoke about how we have cracked one big code of one big puzzle of doing efficient computer vision models, right? And that one thing is called convolutional neural networks. And what are convolutional neural networks, or CNNs, as we call them? They're basically a special type of neural network which incorporate the fundamental aspect of vision, right? The fundamental aspect of vision based on feature creation using localized vicinity aspects and pooling, assembling those later on for a macro view, right? So in CNNs, what you do is you basically, if you have an image, you try to things, and then if you pick a pixel, right? You try to analyze things that are closer to that pixel. You don't want to go too far away. You try to analyze things that are closer to each of the pixel, right? And then you extract some insights from those nearby pixels. And obviously, over a period of time, you refine these insights also. And period of time meaning over a period of multiple neural network layers. But essentially, the idea is you pick some nearby group of pixels, you analyze what is the object contained here, what is the context here, and what are the local features. And then at the end, based on the task that you're trying to do, you pool all these features to get a kind of global or a macro level view, right? So here in this picture we see, so there is this input image of say 28 by 28 by 1. So by 1 essentially means it's a grayscale image. And then we are doing some convolution operations. So we'll not go into what these convolution operations are, but yeah, that could probably be reserved for some future sessions. But these are the crux. This is basically where we come to the crux of things, right? So this is what CNNs are doing. So they are basically creating a lot of feature maps, and these feature maps exploit this principle of kind of looking at things, that are closer to each other. And then at the end, you can see we have this fully connected layer, which is what is exploiting this, nearby features to get a global macro level view. And that is the essential kind of concept of CNNs. Obviously, there are a lot more details to be spoken about here, but we are kind of out of time. So we'll keep those things for the future sessions. But yeah, if you do have any questions, feel free to reach out to me over the channels that I've specified, either over LinkedIn or over emails. And yeah, I've also listed down some more details. So what are the typical libraries? So you have PyTorch from Facebook, TensorFlow from Google, and then there are a couple more. So MXNet, Caffe, and Gluon from AWS. And what are some of the common data sets? So in computer vision, we have two very common data sets that are used for benchmarking purposes. So one is the Cypher 10 or Cypher 100, and the other one is ImageNet. And then at last, the transfer learning models. So we have already spoken about this, basically the ability to create models on larger data sets and then leverage those for your particular task, right? And those larger data sets are generally the ones that come from these two sources. So Cypher and ImageNet are the ones. Yeah, and the references are also posted here. So yeah, thank you very much, and have a nice learning experience here. Thank you.